Thank you for that introduction. Ladies and gentlemen, welcome. Thanks for coming down here to learn about SirenJack. My name is Balint Sieber. I'm the Director of Vulnerability Research at Bastille. And today I'd like to take you through a bit of a whirlwind tour, as I say, about this particular bit of research. I've got some props here on stage that I hope to show you a little bit later in the talk as well. So I'll take you through the overview. I'm going to be talking about emergency warning siren systems in general, the phases of the research, the two big phases there: finding the signal, analyzing the signal, the disclosure process, and suggestions looking into the future. So who has actually heard an emergency warning siren system go off? Can I have a show of hands? Oh, wow. It's quite a few people. I guess they really are everywhere. So as you might know then, the purpose is mass notification of the public in the event of serious emergency. And this is also important where other modes of communication, such as mass text or emergency warning broadcasts through radio and TV, might not work due to infrastructure problems. Tsunami is obviously a common one too. You've probably seen those signs around the place. So those alternatives, you might be familiar with some of them. Unfortunately, there was that incident in Hawaii. You might recognize that screenshot from the press. The emergency alert system is deployed across the US and uses radio and TV. And that's an example of a TV broadcast. So your normal programming would be interrupted and you would see a message on the screen. But sirens and horns and the like have been around for a long time. The old ones originally in World War II, the air raid sirens, civil defense sirens. And nowadays we see a variety of mechanical, not so much anymore, they're slowly being supplanted by electronic sirens. And if you are a siren enthusiast or are thinking of becoming one, then I recommend visiting the Siren board, the one singular place online where every siren enthusiast goes to talk about the subtleties of every model under the sun. It's quite incredible. There's a subculture for everything, and this is where you need to go if you like sirens. So in terms of the mass notification space, these are some of the big players in this space. You might be familiar with some of those brands. Anybody familiar with any of these brands, maybe from the media? And I actually live in San Francisco. So who's heard of the Tuesday noon siren test in San Francisco? Yeah, a couple of you. So there's a ritual, and it goes like this at noon every day. And there should be some audio coming through, so hopefully you'll hear that. So if you move to the city and you're not aware this is happening, the situation I found myself in, it's quite a surprise. It's quite a shock. You don't quite know what's going on, and then you learn about this ritual. And then you have the reassuring voice. Good. So how does the journey begin? Well, this is San Francisco, and I found myself living here and riding to work, and I would hear this going off, and also zooming in, I would ride past these sirens, and they have this little distinctive signature on Google Maps, which we'll see more of later. But I was always wondering, well, how did they work? There's a control box, solar panel, horns at the top of the pole, an antenna. And the security researcher in me was wondering, well, it looks like it's radio controlled. I wonder if it is secure. So I took some photos initially to do a bit of recon and figure out if there were any distinguishing features. I looked at one box and then looked at the other box, and there was a little sticker on the door there. And so I looked the company up. And if you go to their website, this is what it looks like now. It's actually been redesigned in the very recent past. That was a nice high-res picture, but Wayback Machine, that's how I remember looking at it. And they have spec sheets available online, so I looked at that. And they have a couple of core models of their product. And some interesting notes that I found in the spec sheet was that it uses conventional VHF and UHF radio for receiving and transmitting FSK, DTMF, or two-tone sequential signals. There's an optional upgrade for digital and trunked radio systems. But what caught my eye was that in the communication section, it said encrypted FSK, DTMF, or TTS. So I was wondering, well, if it's DTMF, it's probably not going to be encrypted or nor TTS, but maybe FSK, they might have something interesting going on. So remember, this is starting from scratch. I don't know anything about the system, don't have access to the system. This is essentially a fancy amateur radio fox hunt. So the first thing is obviously you need to find the signal. You need to find where these transmissions are going on. But how do you actually find that? Well, I decided to collect some more public intelligence and also look at the radio spectrum. But of course, this turns into a very long-running project because you only get to sample the radio spectrum once a week for a very short window of time. So looking at their spec sheets some more, they have these Siren nodes, 2 models, a central controller that communicates with them, and this can be set up over a simplex radio network where the controller communicates directly, or through a repeater, which can bounce the signal through the repeater and give you a larger coverage area. Looking on YouTube, I found this informational video actually on the vendor's website where this might have been a news, news short, and they talk about the system. They interview people at the San Francisco Department of Emergency Management. And there were always, little choice frames that I found. So there's a map of all of the sirens in the city. And they actually have a very short period in the video where a couple of frames they show you inside the box so you get to see. And what caught my eye was that there was a Motorola radio in the top left corner. It looked like a sort of standard VHF radio. Wasn't quite sure at that stage what model it was. And I should add too that this was initially 2 years ago, actually over 2 years ago now a little bit, when I first moved to the city. So doing some more research online, they have these controllers that would be situated somewhere where the officials can access them in the city. And then the Siren nodes, in this photo from the vendor's website, there's actually a CM200 radio. Comes in 2 flavors, the VHF and UHF flavors. So that might give a hint as to the frequency range. But my thought there was that since this is critical infrastructure, you'd want to have it secured. You probably want to have a large coverage area. So it would make sense to maybe use the city's existing trunked radio networks, of which there are 2. One handy site, if you're interested in looking up licensed frequencies and networks, is radioreference.com. And I had a look at San Francisco, and there were 2 significant public safety trunk networks. One was Motorola Type 2 Smart Zone, the other one's P25. So I thought, well, they're probably worth looking at too because they're designed to cover the entire city, and they might be using that. So they give you the various frequencies that are in use, the various channels to look at, and what have you. And if you actually look at where some of these radio towers are located, then it becomes apparent that they serve the whole city. So it's not an unreasonable thing to guess the signal might be there. The FCC Universal Licensing System has an online database that you can access and do various queries. And so I started doing that, just looking around, guessing that the license for whatever frequency was in use, probably licensed to the San Francisco City and County of. But nothing really very interesting turned up. And I focused on the public safety classification there. You can also look at the station class for these signed frequencies, and if you, again, use radio reference, they've got a nice wiki with all this kind of stuff that can give you a hint as to what type of device or that frequency might be assigned to. But the thing you have to keep in the back of your head is this is often inaccurate. So you have to often treat it with a grain of salt because they might have been in a rush with the application or things might have changed and it might not be reflected in the database. There are also mission designators, and this can give you a hint of the type of signal being used on this frequency, but again, it's just a hint and it's often wrong. So there's a huge list of them, specifies the bandwidth and the modulation scheme and so on. There are also these control points, and they have different addresses, and you could geocode them and figure out on the map maybe if it's relevant to this particular system. And this one, for example, was close to, or at or very close to the Department of Emergency Management, so a hint. They actually have a nice informative page on their website that talks about what the system is, gives you a map, public information. You can actually download that map and know a rough idea of where they all are. They've had false alarms. In 2014, a couple of sirens went off, apparently in the middle of the night. They wrote a blog about it to reassure the public that everything was okay. And it's important to remember that these systems are designed to alert the public, and so the public has to have this implicit trust in them that they will only go off at the appropriate time. So I set about hoovering up large portions of the spectrum. This is a sort of picture of my attic, the old attic, where I had a variety of antennas going, and I had them all connected to Edis Research USRPs. And I started doing some captures. So this is one back in September 2015. I've sort of roughly time-stamped various parts of the research in the top right corner. So just to talk a little bit about what we're looking at here, who's worked with or understands what an FFT waterfall is? A couple of you? So just to run over it quickly, time runs from top to bottom, and we're looking at a chunk of the radio spectrum. So the radio gets tuned to the center frequency, which is in the middle. In this case, it's 850 megahertz. And then, sorry, look into the light. Oh, it's gone. I had to sneeze. It's gone. And then we capture some bandwidth. And here, I think it was, I can't quite remember, maybe it was 12.5 or so megahertz or thereabouts. And remember, we had those lists of frequencies from radio reference. Part of this on the right-hand side is actually the smart zone network. And we're looking at the output channels of the repeater. So you can see all those transmissions there, and I'll show you what they look like in a bit more detail in a second. There's also the P25 digital trunk network. This is another capture that I did. You can see all the transmissions, people, first responders, have their mobile handheld radio, they key up, transmit, and then the signal shows up here at a channel allocated by the trunking network. If you zoom in on that, then you can see the individual digital transmissions there. So interestingly, at around this time, this is March 2017, spookily related to this was the Dallas siren attack. Who remembers the Dallas siren attack? So in this case, late in the night in April, all was 156 odd sirens were triggered as a false alarm, woke everyone up, caused a bit of mayhem, and there was some speculation as to what happened. It looked like it was a radio-based attack. To cover that large area, they might have been using a repeater. This looked like an older system that uses DTMF to activate it, so it's trivial to do a replay attack. DTMF, as you may recall, are those dual tone multi-frequency tones you hear on a phone or even on a handheld radio like this one. If you were to tune that to the right frequency and type in the same numbers, you'd set it off. So if you heard them doing the regular test the previous time, you could record that onto your computer or a tape recorder and then set off the network. So that's what people speculated. Shortly after this, ATI Systems, the vendor that produced the San Francisco system, released a press release on their website entitled, "Is my emergency notification system safe from hacking?" And this sentence stood out to me, which was that many older systems include few, if any, of the advanced security features ATI can provide. So, DTMF is not secure. If they're using their FSK protocol, that might have something else built in. All command packets are protected by several security features, including encryption with AES. So I thought, whoa, okay, that sounds pretty serious. So I might not be able to find what I'm looking for after all. But I pushed on, did some more captures. Again, this is now 855. This is sort of honing in on the smart zone network, and you can see the individual analog transmissions there. So because it's analog, like a FM radio receiver, you just tune to the frequency and you can listen to what's going on. And it was usually just all chatter from various employees of the city and its services. I enhanced it a little bit because, if you do this across a whole variety of frequencies, it's a hell of a lot of signals to have to listen to and scroll through and analyze. So I made the system automatically recognize, detect, and extract the transmissions so that I could just listen to them in order one by one and optimize that process. And every time I did that, every week, I would sort of keep a log as to interesting things I heard. It wasn't going to be anything analog, so I was trying to pay attention to various digital sounding signals. But again, I couldn't hear anything that was of a repeating nature every week. So I looked at P25. P25 is a digital network that uses a digital protocol for voice transmission. And again, you can see a whole multitude of them. And in this particular version of the analysis actually color codes the various parts of a P25 transmission so you can distinguish voice traffic from data traffic from trunking traffic visually. And again, it was just mainly first responders going about their business, keeping the community safe. Kept doing more captures, and at this point, I'm pulling in a lot of bandwidth. So modern software-defined radios can actually receive a lot of and transmit high bandwidth. So here, actually, in this little custom 3D printed case is a software-defined radio. It's a B200 Mini from Edis Research, connects via USB 3 to the computer, and it's capable of receiving or transmitting at up to 56 megasamples of megahertz worth of usable bandwidth. So you can pull in a lot of signal. And here I'm looking at 473 megahertz, 50 megahertz wide, and again, there are even more signals in here. So it becomes this increasing magnitude of stuff to look through. Zooming in there, you can just see how many things are going on. Now, a lot of them, are going off all the time. You want to find some correlation with the noon activity. Looking elsewhere in that band. Remember, these frequencies now are actually compatible with that Motorola radio we saw in the spec sheet before. The other thing is if you're doing captures, it's very important that you have good RF filtering. So this is without RF filtering. You can see there's a lot of out-of-band interference coming in there. Looks like it might be LTE traffic from nearby base stations. But if you put a filter in, it cleans it right up and you can get at weaker signals underneath. I also found another informational video. This was the older style controller. So what to look out for. It gives you an idea of what the user interface is like, what the system looks like. This is a portable pack that you can use to activate the system. And then, they show various screenshots of the software, so you can get a sense of how that would be controlled through the software. Apparently, these Siren nodes can have different states, which comes in later. I did some further surveying where I went up around San Francisco looking for more of these Sirens. And again, trying to find the frequency from another angle, tried to look at the antennas that were in use because they can sometimes give you a clue as to what frequency they're tuned for. An antenna is usually tuned for a narrow range of frequencies. So I had a look and really they were all like this omnidirectional antenna. And the thing is, you learn that for a particular frequency, there's one specific wavelength and you can have your antenna at that wavelength or some proportion of it. That doesn't necessarily apply here because such a whip-style omni might actually be comprised of collinear stacked elements inside the housing. So if you can't see through the housing, you have no idea what's inside. And so it really could be anything. So that wasn't particularly fruitful. And I thought, well, I'd like to get a measurement on this. I can't climb the pole. I'm not going to bring a ladder. So I tried once when I was riding my bike to pull up by the pole, and then I used a tape measure to measure the shadow on the ground that the pole was casting to figure out the circumference of the pole, and then use the relative pixel ratios in the image to extrapolate the approximate length of the antenna. And as you do that, you quickly come to know that there are intrinsic parameters of your camera lens that will distort the image as you move in and out. And so any extrapolation of pixels to physical length quickly becomes quite inaccurate. But it was worth a shot. And then this was me attempting to try to get some other angle on it with my camera, not being terribly successful. But you're trying to be a little bit inconspicuous about it, right? So I did more captures. Now this was at the lower end of the spectrum that radio supported at 155. All manner of signals in there, and there's a very, very strong TV, digital TV transmission in there as well. So this one week I happened to start late, and another one started early. I was, trying to coordinate captures between 3 computers and antennas and stuff, so couldn't always get it happening. Did some research online about the antennas, tried to find antennas that looked similar to the one that I saw in the photos, eBay listings, Amazon listings, other listings. Tried to measure the proportions here again, the relative pixel ratios of what I found in my images versus online. And then I found the catalog. These antennas really look like the same ones. And these would give you the frequency ranges and the antenna lengths, and using that as a basis to try and match it up to the photos. Again, nothing really quite fit. And then I went all out, and I spent, it felt like days, on Street View, using that public map as a reference, trying to find everyone that I could in the city to try and get as many Street View samples of the pictures of the antenna so that I could build up some average of the antenna proportions and match that against the PDF. And again, didn't quite work out. So I just started mapping them out on Google Earth so I wouldn't duplicate my efforts. And they do cover quite a broad area. And then I had seen this many months ago, and at 2 a.m., I just sat there in bed, really not knowing what else to do, and I watched it again. And again, there are these choice, this is another informational video, other choice frames. Again, this is the software with the map of the city on there, the individual Siren nodes, and different coloring, I'm guessing, indicating status. This looked like it was the dialogue that they clicked to actually activate the sirens at noon. And again, this is the corner of that control unit, so was a good clue as to what they were actually using there. And then this frame flashes on screen for, I don't know, less than a second. And it never occurred to me, and then at 2 a.m. I sort of freeze framed it, and then I realized there's a clue here. I've highlighted it, but anybody can guess what it is? Louder? There's a Yagi antenna there. A Yagi antenna is a directional antenna, and its characteristics are visually far more obvious. So I thought, that's great. Where is it? Because there are, over 100 in the city. So again, I hopped back onto Google Maps, and of course, you can use satellite view. You can see the interesting little footprint, but you need to go into Street View for every single one of them to find this Yagi antenna. And actually, I got lucky, and just after a few trials, I found it. It was one up from the series that I found on the western side. So I went there and pretended to be a tourist with my camera. Oh, Ocean Beach is beautiful. Look at these people. It's a nice cloudless day. There's a big ship departing the port. Oh, and look, there's a Yagi antenna sticking off a siren pole. And I got in nice and close, as inconspicuously as I could, and I thought, wow, look at that. 3 elements. You've got the stepped lengths. You've got an interesting thicker part of probably the driven element in the middle. Really good features, and there's a sticker on the right side there. Couldn't get a photo of the sticker, but that was okay. So then I set about, and then I went home and took more of my own photos in case I needed them of the omnis. And then I used a compass also to figure out where it was pointing, and then drew these rays, in some error margin, and it was pointing at the middle of the city, and they have radio infrastructure up there. And I thought, well, if it's there, then maybe that would be the place to communicate to all of them from. And if you look at that, this is actually Twin Peaks. This is 3D view in Google Earth looking back. And so that Yagi is behind that hill. So it makes perfect sense they would have used a Yagi, because they would have needed a little bit of extra gain to get over the hill that was partially obstructing the view. So that fit. And the radio transmitters turned out to be not on Sutro Tower, but they have 2 other smaller towers there that has a lot of infrastructure. And actually there's a siren horn on top of the building there. So then it was a matter of trawling through every single antenna manufacturer's PDF that I could possibly find. There were a lot, and eventually I found it. 2 candidates, very close in band. And if you put the one I found there, then that looks like a pretty good match. So it's a much smaller part of the frequency range to look at. As it turned out, I went back and I looked at the captures that I'd made, the ones that I started early and late. And there was this activity that lined up with the midday test. I couldn't believe it. And then in the one that I also captured, this was, I think, a little bit early, because I'm capturing so much data, I'm using a RAM disk to stream all the data in, and of course you only have very limited time and space when you're using RAM disk at that throughput. And what was interesting, I looked closer, is that you could tell that a repeater system was in use. This is the output on the right, input on the left, and you can actually match up the transmissions that occur from the control unit that they had maybe at the Department of Emergency Management versus what look like responses from the different nodes. Because if you look at the second part of each group, there's one which is sort of a standard signal strength, and then the second part varies. So that one is, sorry, the one that is just about to be highlighted now, that's strong. That one's the ping, that's the pong from a node. So I was guessing this is a sort of a polling response where they would check the status after the test. And then that one's quite weak, so that was further away from my antenna because I'm receiving both the input and the output. And then if you're really interested, the repeaters by law need to announce their call sign in Morse code at regular intervals, so you can get the call sign that way. And so then every Tuesday at noon, this would be the ritual, you'd hear the signal go off. There you go. A little bit closer. This is the radio. So what's interesting is the audio you're hearing is actually coming out of this thing too, which means that although they're using FSK to make it compatible with existing analog repeater networks, conventional audio, they look like they were probably using AFSK, so that's audio frequency shifting over a normal FM link. So that means a radio such as this, $30, can be used to do the transmission and reception. You don't even need to use a software-defined radio, just the headphone and mic jack from this thing. So found the signal, great. Well, we have to figure out what's in the signal. So every Tuesday at noon then, every single week, I would record, create my plots, and then begin peeling back the layers. So I would use GNU radio, and I have a flow graph that went through many stages of development, and it would stream the audio into there. And as I peeled back the layers of the protocol, I could print out the various things I could make sense of. So this is the flow graph. Some of you may have seen my flow graphs before. It's good because if you hide the disabled blocks, it looks a little bit cleaner. But this is actually, I decided to go all out and make an optimal non-coherent 2FSK decoder with no clock recovery because the length of the packets is so short that your clock drift would never cause the symbol boundaries to cross. So that was, that makes it a little bit simpler from clock recovery point of view, but I had the two branches for the two tone levels and what have you to make it more robust. So if you look at the physical layer, this is again a waterfall. This is the raw baseband, and this is audio FSK over FM. You can see you've got some sort of sync preamble, you've got the payload, you've got some idle filler that happens at the end. And then once the modulation disappears, you're only left with the CT-CSS tone that's used to key up the repeater, to get into the repeater. It's just a sub-audible tone that is shared by the system. And then you've got the repeater tail where there's no modulation. If you FM demodulate that, then again in the frequency domain, this is the filter width that I applied, where the top and bottom, that's just unmodulated RF. It's clear that you have two tones that are used to convey the bits, and those two tones are actually standard tones for 2FSK. Again, you've got the preamble, your payload looks like in three parts, a post-amble filler, and then just the CT-CSS tone. And if you look very, very faint line on the left, that constant line that's running through from top to bottom, that's the CT-CSS tone that you need so the repeater lets you in. What does that look like? So if you change your parameters, you can see the modulated data there. Again, this is in the frequency domain, but you can see the two levels jumping back and forth for those bits. So I took a sample, put into Jupyter, and very clearly you can see the two levels there. If you slice at the 0 line, Anything above at a certain time is a 1, anything below is a 0. And then you've got your 1s and 0s. But you need to know how quickly your 1s and 0s are coming through the system, so you can do some simple cyclostationary analysis. And it sounds hard, but it's not. You basically multiply the signal by a delayed version of itself and then take the Fourier transform. And then the strongest peak is usually the periodic rate of the signal. And here, it was 1200 baud. So, 2 tones, 1200 baud, all very standard stuff. So we know all this about the physical layer. I started getting raw bits out, and you'll notice that there's this kind of odd alignment. There's a pattern there for sure, but if you look around the middle where you've got the long strings of 1s, they don't quite line up. So I didn't know what was going on there. But if you sort of start playing around in text editor, you can line things up a little bit, make it look a lot nicer, and you've got these extra zeros that turn up. And if you think of serial, line protocols, often you have a start bit and you have some idle time before that. So I figured it was either that or some other level of security. And then turning that into hex, looked like there was a good repeating structure coming out. And then looking at them, well, you got long strings of 1s, so maybe that's not good. Try some inversion. And then things started looking better. So these were the 3 packets that were sent out before the sirens went off on Tuesday. And they all look the same apart from just a few bits changing. And then on another week, a lot of things look the same, actually. So that was a little bit of a cause for concern. So the other interesting thing was, apart from the activation, those trigger packets, I called them, and the polling and response after the test, around about every 20 minutes, these packets would go out. And pretty regularly, 20 minutes, so I thought, well, maybe it's some sort of a keep alive mechanism. And maybe there's something changing in there, like a time every 20 minutes. So it wasn't obvious how things were incrementing or decrementing, and I sort of, there's a copy of my notes there, the things that I identified as patterns and things that were static and not. And I thought, well, hang on, maybe I've just packed the bytes the wrong way. So I'm going to pack them in the opposite order. And then what do you know? You've got incrementing values during your trigger sequence. So that's a pretty good sign. I mean, worrying, but good sign in terms of analysis. What about CRC? Good to know that the data that you're dealing with is solid. So I tried CRC8 because, if you look at the last bytes there, they're the ones that are changing on the end. Usually the CRC is appended. And there were no hits with CRC8. There's a neat tool called reveng. It brute forces all sorts of CRCs with different polynomials and settings for how the CRC is computed, no hits. And then I thought, well, let's try something super simple. I've seen them do this before in other embedded systems. I just summed up all the bytes, modded them by 256, and bingo, that was it. So in terms of the timestamp, I just kept collecting more data of these announcements, and I could see that there were these values that were incrementing at a predictable interval. So initially there, I plus whatever is the offset, I was taking 2 bytes, but then I just started looking at the 1, and you could see when seconds would roll over, the minutes were very, very clearly rolling over, and then the hours as well, and then even the days. And this is not synchronized to real world time. The system is running on its own time domain, but at a normal second rate. And then again, other elements of it rolling over. So it's quickly becoming apparent to timestamp. So we've learned these things about the packet format. They repeat the payload 3 times for redundancy, and they have that serial protocol still in there. So there's a proprietary protocol, and often, as is the case there, what happens is security, maybe unintentionally, security through obscurity. So this is time announcement, and interestingly, when I looked, there was no transmission into the repeater for the time announcement. It was only ever an output. So that would indicate that there was actually another controller of some sort at the repeater to send out this time announcement. So it became clear that really there was no security. You could very clearly see the clock incrementing, and you could very clearly see the sequence that's used to test them off. So a malicious actor could take this knowledge, extrapolate the time, and set the sirens off whenever they want. And that was of a concern. After the test, the controller polls each node and does that ping response. And it was interesting too, because whenever I would watch this each week, I could see, if you look there, if you can see that there are incrementing node numbers, so it pings each one. But then sometimes it wouldn't be able to reach a node, so it would retry a number of times, and then it would move on to the next one. And so it was kind of interesting being able to get a sense of the state of the network, because the people in the city would have been watching this and going out to repair them, but you could also get some sense of what was going on as well. So everything looked like it was in the clear, no encryption or secure authentication, and you could extrapolate the values. So did this week after week, and then the other part of the time stamp, the month and day quickly became apparent. If you look from bottom up, you can see it incrementing that way. And then my decoder wasn't perfect either. Sometimes it wouldn't be able to decode a packet. I tried to make it fancy by doing this sort of tree search, because if you think about it, if you get a corrupt bit, you need to know where the start bit is for the next byte. And if you get a corrupt bit, you might start too soon, and then everything after that is corrupt. So it would try this tree, I can't remember if it was depth or breadth, but it would try to go down until some limit to brute force out a packet. Sometimes it would work, but often it would tell you couldn't find a valid frame. And I thought, well, it'd be cool to also to overlay on top of the waterfall the elements of the packet and whether it passed CRC. So that way I could tell, basically if I was able to receive the signal properly and, where I might need to do more work on the decoder. Interestingly, well, it was sad news, but there was a break in the pattern. One Tuesday there was nothing. And unfortunately, that was the day when our former mayor passed away. So they didn't run the test in honor of him, but it was just interesting to see the break in the pattern. So with this knowledge, obviously we were very concerned. We don't want critical infrastructure systems to be vulnerable to this sort of exploitation. Even though this is not a replay attack, you can see how it would be, in a sense, much easier to craft malicious payloads like this. So we set about doing our responsible disclosure, and our policy is a 90-day disclosure policy where we contact the vendor, offer our assistance, give them all the information we have, and try to work with them as closely as possible or as close as they like, so that some sort of remediation can be put in place, a patch can be created, and then we inform the public so that if something hasn't been made available to them, they can make their own decisions about how to secure their system so that they're not at risk. And this is pretty industry standard. A lot of folks have much shorter time frames, but this is generally well understood that this results in action and helps all parties at the end of the day. So in terms of our timeline, we notified the vendor on the 8th of January. We also notified the Department of Emergency Management because they were looking after the system, so we thought. And then 90 days later, we released our public disclosure on April 10. And at that time, the positive outcome was that the vendor ATI had created a patch and provided to at least one customer, obviously the city. And I'll show you how that looked as well. But initially, it took a little bit of effort to try and get people's attention. We found this with our previous disclosures as well. So we first tried via email and phone calls and more emails, trying different departments that also might deal with it via telephone, trying external affairs, the press office, and we actually did a sit-in. My former colleague Matt, who's sitting there with his hand up, we sat in there and tried to find the appropriate senior people to make sure that they understood that this was an issue, and we were trying to get in contact with them and doing our best to do so. So we ended up leaving a hard copy there. Also tried, looking at how we might contact ATI engineers. They looked like they were in different time zones, so that wasn't going to be easy. We kept on because we hadn't really heard any confirmation yet. So we got our first email back from the DEM it turns out that the Department of Technology manages the infrastructure, the outdoor public warning system. So they forwarded our email to them. And then I also tried to chase down an employee that I found publicly had been previously affiliated with the project. And again, Matt and I went to the new department where he worked and also a remote location and tried to, physically find him and email and phone him and the supervisor. And then we called ATI again. They couldn't guarantee that our call would be returned. We sent more emails. And finally, in February, we had our first call with ATI. And we established a dialogue, and they said they'd look into it and talk to their engineers. And then we had a call from the Department of Technology, and they were in contact with ATI at that point. So that was good news. Then later in February, we had our first proper dialogue with the Department of Technology. ATI said they were working on it when we tried to call them. We received a formal letter from ATI later that month, and then we had further phone calls with the Department of Technologies just to find out how things were progressing. And then we requested the vendor response for the public disclosure by email, by letter, and then by email. We finally received one later in March, and then we worked together to come up with the final version. An excerpt of that was that they recommended, if you wanted highly secure encrypted links, to use P25, to use the trunked radio upgrade, as well as the fact that they had created a patch which adds additional security features to the command packets sent over the radio. So that sounded good. Meanwhile, while this is all going on their website, if you would look, they had a number of featured installations. So we were interested in finding out whether was San Francisco unique or were other people also potentially affected by this vulnerability. So, we looked around online, and this was the old version of the website. This is the new one. And again, different customers in different markets there. Plotted them out on the map, cross country. On LinkedIn, it also says that there are thousands of worldwide installations of this equipment in operation today. And that one that was highlighted in their featured list was Sedgwick County, and they had malfunctions as well. And they did this little video report. So as I play this, we've heard what the command packets look like, what the 2FSK looks like. And you saw that it wasn't trivial to find out the frequency of the system. Have a look at the video.
Caused them to malfunction.
Probably in the water.
And I thought, well, let me take the audio from the video and try and demodulate that. So here again is the 3 repeater payloads with the idle filler. So it looks like the system that we found. I couldn't get the raw ones and zeros out because obviously the audio gets compressed when they put it online, and so that destroys the two tones. But they have a map of their sirens in the county there. I tried to visit it again, but that's 404 now. That frequency that was on the sticker that was on the radio is registered in the FCC ULS. You can go to that address on Street View, and sure enough, there's a big honking antenna in there, so they probably have a small antenna on there. So I flew out there, booked at a hotel, and made sure that I got a room that was facing the antenna so that I would optimize my reception. And took a little bit of a tour, and sure enough, they had the installations out there. And again, there are warning signs. They're trying to be a bit inconspicuous there if they've got everything on camera. And this is my hotel room getting ready, because they also do these regular tests. And they have a different tone for their siren. It's just a constant tone. But I got it all tuned up there. Multiple laptops for redundancy. Multiple SDRs, all looking good. And unfortunately, same deal. This was a little bit different from San Francisco. There was some subtle difference, but there was enough similar here that we decided to, I called up the relevant folks in their county, and it's a little bit difficult because if you have someone cold calling you saying that we think we found a problem with your system, it's perfectly reasonable to say, well, if there's a problem, we'll hear from the vendor, and if there's anything crucial, send it to us in writing. And we did that. And then it turned out, a while later, we heard that they were in touch with the vendor, so that was good. Also, we managed to procure some of the equipment, because at this point, I hadn't actually had physical access to it before. And when you do your own tests, obviously you don't want to wake the neighbors up, but also you don't want to transmit into the air over unlicensed frequencies. So I got a big fat attenuator because there's quite a bit of power coming out of the radio here. And instead of using this massive speaker, I thought, well, maybe I'll hook up a little 8-ohm speaker and maybe it'll figure out there's a small load on there and adjust. And I hooked it up, and of course the magic smoke came out of the speaker. But the good news was I was playing around, brute forcing stuff, playing around, looking at all the data that we had, trying all sorts of combinations, and then I managed to get this. Now, I had that 8-ohm speaker hooked up, and I thought it was coming out of that, because I wasn't going to have this big honking thing hooked up. And what I realized a little bit later on was that audio is actually what I believe is the thermal changes in the big transformer in the amplifier under the board there as it's having the huge amount of power pushed through it. So there's no actual diaphragm or anything moving to produce the audio. It's the vibration of the electronics in there that's emitting this audio as well. So there's there's quite a bit going through there. So we did an outdoor POC. You might have seen that. I'll skip that. And then toward the end of our disclosure window, things started happening on air that I couldn't have possibly imagined because I was just so used to listening to those tones. Have a listen. A human voice. Couldn't believe it. So that was good. And funnily enough, my friend from Australia who happened to be visiting just for a few days, he was in Union Square. He thought, oh, we're both like radio. He took a photo just totally out of the blue, unaware of the research, obviously. And they were going around to all the Siren nodes and presumably applying the new firmware to make it aware of this new protocol that they would be using. And I saw over the weeks, you can see the green sections. They're the packets that I've analyzed and my decoder recognizes, but there's all this failure now, all these red ones. And I'm sure that the bits were coming out fine, but they had changed the format. So zooming in there, you can see, there are still some known trigger sequences, but the other ones are not known anymore. And then come the day of the public disclosure, everything was red. So they changed everything. I haven't looked into it in detail, but if you look at the values on the side there, they're all, they don't have structure anymore. So that's good. And we also worked with ICS CERT and had an advisory listed there. And it was also nice to see just very recently in the Wichita Eagle, they rolled those fixes out there amongst the network. So just to wrap up then, suggestions. You need to design in RF security from the ground up. It's very easy to overlook. Tools such as these software-defined radios, open source software are cheap, easily accessible to security researchers, enthusiasts, and bad actors, especially if they're well-funded. Radio-enabled critical infrastructure is everywhere, and it has to be scrutinized. If you have an obvious way for people to get in touch with you if they think that they've found a problem. So, commonly there's an email set up with a PGP key and so on. That has to be done for anybody that has this sort of equipment. The radio spectrum is a shared medium. As soon as you jump from anything on the wire to over the air, it's accessible to anyone. That's a very important thing to bear in mind. So you cannot rely on security through obscurity anymore. And then if you are disclosing, strictly adhere to some robust process that you design ahead of time. Thank you for your attention. For more information, you can go to the website or the ICS details. I want to shout out a big thank you to Jay Branscombe. He was my boots on the ground on the East Coast, capturing spectrum and doing some experiments out there. And also Neil Pandy and Nate Temple, who's sitting here in the front row, they were my emergency response team when I couldn't get the power supply working for my demo, so they rushed over here with a new power supply. So I really appreciate your help. Thank you very much. And also want to thank my colleagues at Bastille for helping me and supporting me through this, especially in the disclosure process. Thank you for your attention. And I might try to get this going if anybody has any questions in the meantime.
So you want to do questions afterwards, or do South Pacific B?
South Pacific B, great. See you there if you have questions. And I've got my little thing running here. Let's see if it'll actually work. So this is showing what's coming back from the radio. Just going to start up the little program here to hopefully start that Rickroll mode. All right, so now we're going to, let's see what's going on here. Okay, so I've activated the public address mode. So I just sent a packet out there, and now I'm going to launch another program that's actually going to send, it's waiting for a new signal to come in, which is the modulated FM audio that it's going to output over the speaker. So I'm going to launch that program now. There we go, so it's running. This is just a little transmitter app for the audio. And then I can slowly turn the volume up here. So that's it. Thank you very much.